Welcome to the Professor's DuBois channel. This is Professor Corey, and this video is a mini lecture based on our first lecture covering material from Chapter 8. Before we dive right into Chapter 8, we did a little summary of Chapter 7 and the periodic trends, which we kind of captured on this slide here. So we have three trends that trend the same: the ionization energy, electron affinity, and electronegativity. And these trend toward the upper right. So they increase as we go up the periodic table or go to the right. And there's two trends that are just the opposite. That's the metallic character and the atomic radius. When we begin Chapter 8, we're going to spend a lot of time with chemical bonding. So we took a little time just to talk about what a bond is, and we can define a bond as an attractive force that holds two or more atoms together. And there's actually several categories of bonds. These are listed below, and we're going to primarily focus on the covalent bond, or the sharing of electrons between atoms. And this typically exists with nonmetal to nonmetals. Our valence electrons are our bonding electrons. So it's going to be really important that we can figure out which electrons are valence electrons, or how many valence electrons each atom has. Gilbert Lewis came up with a method for writing the valence electrons around a chemical symbol. This is called a Lewis dot structure. So the symbol itself represents the core electrons, while the dots around the symbol will represent the valence electrons. So you can see in this diagram here, for boron, we have three valence electrons. Those are the electrons in the highest N, the highest energy level, the 2 in this case. And so we put those dots around the symbol B. The symbol represents the core electrons, which are the 2 electrons in the 1s orbital. Bromine is shown below. Bromine has 7 valence electrons, and these are represented as dots around the element. And notice how they're arranged in pairs and kind of in quadrants. This is a correct way to show these dots. We wouldn't put all 7 on one side of the element. In the order in which we fill these is not important, like it is when we're doing electron configurations. So you can see here we've got the Lewis structures for these elements, and the arrangement of the dots is a little crazy. In particular, like this carbon atom here, I would put 1 dot in each of the 4 quadrants, but this is okay too, as long as we don't do more than 2 in a certain quadrant. And something else worth mentioning on this slide is that we can quickly determine the number of valence electrons just by looking at the periodic table. And up at the very top, where the groups are listed on your periodic table, they're maybe written as 1A, 2A, and then boron being 3A. Might not be. Boron might be 13 in your periodic table, in which case we're counting every group, including the transition metals. But it's fairly common to see the 1A and 2A, and then we just skip the transition metals. Boron would be 3A, that whole group. Carbon would be 4A. And what's really convenient about this is that number is the number of valence electrons for that entire group. So the carbon group 4A, carbon has 4 valence electrons. And I can move down that group. Silicon, 4 valence electrons. Germanium, 4 valence electrons. So this is a really fast way to know how many valence electrons there are. So a covalent bond, we said, involves the sharing of the 2 valence electrons between the atoms. So we've got this diatomic element here, chlorine, and we can see it. We have 7 valence electrons. So we have we have a half full 3p orbital in each of these. And if these p orbitals could overlap, then they could share the electrons, and each of them would think that they had an octet in this case, or 8 electrons around them. So this is representing with the dots, and down below you can see how those p orbitals might overlap so that these electrons can be shared. So there's often electron pairs that aren't involved in bonding. We call these lone pairs, or sometimes you'll see non-bonding pairs as opposed to a bonding pair. So a bonding pair, it represents a single bond. That's 2 electrons in a single bond, and sometimes that's shown as like a stick. You can see that down here with the HF. There's our single bond. So we can have a double bond, which would look like 2 sticks, and this would represent 4 electrons. Triple bond would be 6 electrons, and these are all bonding electrons. Some other terminology here. We have a shared pair is the same thing as a bonding pair or a bond. Central atoms, there can be more than one central atom, but central atom is bonded to more than one thing. The terminal atoms, they're kind of on the outside, and they're just bonded to one thing. So we got a couple rules here that they're coming really handy. These would be great things to review. And the first rule is hydrogen can only have one bond. It has 1 electron. It's in the 1s orbital. If it bonds, if it shares an electron with something else, it has a full 1s orbital. It has a noble gas configuration. It's content. So this is one example. Halogens, these are in group 7a or group 17. If they're terminal, they will only form a single bond. And this is a really powerful thing to know as we move ahead. The period 2 elements, so we're moving left to right across the period, they can have at most 8 electrons around them. Important. When we draw Lewis structures for compounds, there's a set of rules, and we have this set of rules as a handout. If you don't have the handout, you can probably read this here. And if you follow these rules, you can draw perfect Lewis structures every time. But what happens is you start to get comfortable and you'll start to draw Lewis structures incorrectly. So keep following those rules. Don't assume you know it until you really know it. We've got some examples here we did in class. We showed how when we do the Lewis structure for nitrogen, when we follow the rules, we don't have enough electrons to complete the octet. So what we're going to do is turn a non-bonding pair here into a bonding pair. We can do that, and now we have a double bond in here. We still don't have an octet for this nitrogen. So the way around that is to turn another non-bonding pair into a bond, and now I have octet for both of these nitrogens. So I've got 2 electrons here, and then I've got 2, 4, 6 in the bonding. So each of these nitrogens has an octet. There's some more terminology here. A sigma bond is a single bond is called a sigma bond. A double bond, there's 2 of these sticks, and we call one of them a sigma and one of them a pi bond. And it's not important which is which. It's just one's a sigma, one's a pi. Now for a triple bond, like with our nitrogen example, that we have 1 sigma and 2 pi bonds. And again, it's not important. We don't specify that this one's the sigma and these 2 are the pi. We've got some exceptions to the octet rule, and there's a term you'll hear, it's called electron deficient. And what this means is that we have less than 8 electrons, less than an octet. So 1 is hydrogen, and that makes sense because this only forms 1 bond. 2 shared electrons, that 1s orbital is full. It's got a noble gas configuration similar to helium. Beryllium will be content with 4 shared electrons, or just form 2 bonds. So it doesn't satisfy the octet rule, but we see compounds in nature where beryllium just has 2 bonds, and boron exists with just 3 bonds. Some other things that you'll come across are free radicals. And free radicals are compounds that have an unpaired electron, so just a single electron. Very reactive species. They're looking to either pair. They're looking to pair that electron up or get rid of it, and makes these very, very reactive species. And another thing you're going to see is when we get to the 3rd period or below, so meaning 4th, 5th, 6th, 7th period, the central atom can have more than 8 electrons. So, and this comes back to that d orbital. Once we get to the 3rd period, or n equals 3, we have the d orbital. So this d orbital can be used in the bonding as well. We did an example here I guess we did a couple examples. We did water on the left and the PBr5 on the right. So just following the rules. Hopefully you can follow through the rules and see what we did here and draw these on your own. And just one thing worth mentioning is down here, this phosphorus, it's like, what about the octet here? 2, 4, 6, 8, 10. 10 electrons are on that phosphorus. So if we look on our periodic table, that's in period 3, so that's okay. That's what we call our expanded octet. These are the answers to those previous, well, I guess they're still here on this slide. So you should be able to draw these, follow the sheet, just keep following the sheet, even though you start getting comfortable with it. You're going to want to practice these a lot. Maybe try to work through these following the sheet, and after you've done them, maybe try to do them without using the sheet. But take advantage of that sheet. You'll draw beautiful Lewis structures. Keep practicing, and thanks for watching. Give the video a thumbs up and subscribe if you'd like to see more mini lectures on the Professor's DuBois channel.